All right, so let's say we have a function like this. F of x is equal to x to the fourth plus the square root of x plus 1 over x to the fifth. And I don't remember, you guys, maybe you can remind me. Did we get to antiderivatives at the end of 17a? I feel like maybe some people did and some people didn't. I see a couple no's. That's all right. Okay. I see not in guy. All right, cool. I mean, we're still gonna talk about them anyway. I just was wondering if people have them. Okay. So antiderivative, all you're trying to do is look for the function that if you took its derivative, you would get this function back. So often we're kind of thinking of this function here as our derivative. So this is like a g prime of x. So this kind of like a trash. And we're trying to find g, the function that you take the derivative to get this. So for powers of x, it's actually relatively simple. In fact, what we want to do before we start trying to think of the antiderivative is rewrite the square root of x as x to the 1/2, and rewrite 1 over x to the 5th as x to the -5th. Because I know a function whose derivative is x to the 4th. I hate being so far off board. I know this. Sorry, let me move my board. Okay. Yeah. So I'm going to think of the antiderivative, and usually when we're still using this language of antiderivatives, we write the antiderivative of a lowercase thing as an uppercase thing. That's not always true, but it's often pretty standard. So I'm going to find capital F of x, or you can think of it as g of x. So that the derivative of this is equal to this. The antiderivative of this is equal to this. And antiderivatives and derivatives always have this kind of back and forth where, yeah, if you take the derivative, you go from here to here. If you take the antiderivative, it undoes the derivative. You get back to where you started. I want a function whose derivative is x to the 4th. It's going to be kind of like x to the 5th, but not exactly, because the derivative of x to the 5th is 5x to the 4th. We don't need that 5 coefficient. We need to divide it away. So the antiderivative of x to the 4th is x to the 5th over 5, because the derivative of x to the 5th over 5 is 5x to the 4th over 5, which is x to the 4th. And then the same sort of thing is going to be true here. The antiderivative of x to the 1/2 is going to be x to the 3/2, but not quite, right? Because the derivative of x to the 3/2 is 3/2 times x to the 1/2. Right? I'm just using the power rule. So I don't want that 3/2 coefficient, so I'm going to divide by 3/2, which I'm going to fix in a minute. And then similarly here, I want something whose derivative is x to the -5th. Well, again, the power has to be 1 larger. That's going to be x to the -4th. And one more time, the derivative of x to the -4th is going to be -4 times x to the -5th. I don't want that -4 coefficient, so I have to divide by -4. Now, this doesn't look exactly as nice as we'd like it to. We would like to, you can either write this as x to the 5th over 5, or you can write it as 1/5 times x to the 5th. You can write this as dividing by 3/2, the same as multiplying by 2/3. You can write this as plus 2/3 x to the 3/2. And then dividing by -4 is the same as multiplying by -1/4. So you can write this as minus 1/4 x to the -4th. Now, this isn't quite the whole answer. It's mostly the whole answer, but we need one more little thing. And that one more little thing is that I could add on any number, because the derivative of 6 is 0. Right, Michaela, I need a plus c to account for the constant that could be there. So when we're finding an antiderivative, if it's not an initial value problem, we're finding general antiderivative, there's always this plus c, because the derivative of a constant all by itself is just going to be 0. So what we did here was essentially what I like to call the reverse power rule. Right? If your function is x to the n, then your antiderivative, well, in each case, the power got to be 1 bigger, right? 4 plus 1 is 5, 1/2 plus 1 is 3/2, -5 plus 1 is -4. So our new antiderivative is going to be x to the n plus 1, but then we ended up dividing by that new power in each of these cases. Plus c. So that's what I call the reverse power rule or the anti-power rule for antiderivatives of powers of x. Should be noted, this doesn't work for n equal to -1. Because if n was -1, you'd have x to the 0 divided by 0, and dividing by 0 is undefined. We'll talk about the -1 in a minute or two here. Let's see. Just want to take a look. I wrote down a whole bunch of stuff. Yeah, okay, we're good. So again, feel free to jump in if you've got a question. I'm going to give myself a little more room here to see what I'm doing. Cool. So the real deal is that basically any function you know how to differentiate, you know how to antidifferentiate the response. Meaning, let's say my function was this. Let's say the derivative, just to kind of use different language. Let's say h prime of x is equal to 4x to the 6th plus 5e to the x plus 6 cosine of x minus 7. And I want to find the antiderivative, which is just going to be h of x, right? If this is the function, its antiderivative is this, or the derivative of this is equal to that. So, right, from here to here, you take the derivative. From here to here, you take the antiderivative. Same deal on the previous side, right? From going from here to here, you would take the derivative to get from there to there. To get from here to here, you would take the antiderivative. So always, always true. All right. So for the powers of x, we're just going to use the same idea, right? If you've got x to a power, we're just going to add 1 to the power and divide by the new power. So the antiderivative of 4x to the 6th should be 4x to the 7th divided by 7. And that makes sense, right? Because if you take the derivative of this, the derivative of 4x to the 7th divided by 7, well, if it helps, we can write it as the derivative of 4/7 times x to the 7th. And you're like, oh, I've got a constant multiple. Constant multiple just hangs out. That's going to be 4/7 times the derivative of x to the 7th, which is 7x to the 6th. And then the 7's cancel, and you get 4x to the 6th. So totally works, just making sure it works. But then we have some other functions that are not powers of x. We have to remember, do I know a function whose derivative is e to the x? We definitely do. It's e to the x. It's its own self. So the antiderivative of 5e to the x is going to be 5e to the x, because the derivative of e to the x is e to the x. And constant multiples just hang out, whether you're differentiating or antidifferentiating. Right? The derivative of 5 times e to the x is 5 times the derivative of e to the x, which is also 5e to the x. Come on, chair, get out of the way. All right. This one always trips people up. What's the antiderivative of cosine?
Sine of x.
Exactly. Positive sine of x. Right? We know the derivative of sine is cosine, so we know the antiderivative of cosine is sine. And then what's the antiderivative of minus 7?
7x.
Right. Minus 7x. So whenever you've got a constant, you just get to slap an x onto it. If you wanted to, although you don't need to do this, you could think of it as being 7x to the 0. So that when you do the reverse power rule or the anti-power rule, you get 7x to the first divided by 1. But no one really writes that. But it is still a valid way of thinking of it. And then finally, plus c. And that would be our antiderivative of this mess here. Okay. Yeah, gotta be a little more just with my space usage here. So let's look at another example. Let's say I wanted to find the antiderivative of this function, f of x equal to x squared plus 3x times x plus 4. And what I really want to say here is that we can't find the antiderivative of this just by taking the antiderivative of each part, right? It's definitely not going to be x cubed over 3 plus 3x squared over 2 times x squared over 2 plus 4x. Right? We can't antidifferentiate a product by taking the product of the antiderivatives. Just like we can't take a derivative of a thing, of a product, by taking the product of the derivatives, right? You would have to use the product rule to take the derivative here. So what we're going to do here, instead of trying to think of a fancy way of doing this, we're just going to multiply it out and then antidifferentiate it. People say there isn't a product rule for antiderivatives. That's technically not true, but essentially it's not true. So we don't have a product rule for antiderivatives. It's meaningful in the same sort of way that the product rule for derivatives is. So to antidifferentiate this product, we're going to multiply it out. So you get f of x equal to x squared times x is x cubed, x squared times 4 is 4x squared, 3x times x is 3x squared, and 3x times 4 is 12x. And then we might as well combine those like terms, right? So that's x cubed plus 7x squared plus 12x. And now we're ready to antidifferentiate. And again, these are all powers of x, so we're pretty set. The antiderivative here, is going to be, so again, I'm just using the power rule, the reverse power rule. Add 1, divide by the new power, x to the 4th over 4, 7x cubed over 3, 12x squared over 2, which is going to reduce to 6x squared, plus c. And that's it. Let me do one thing here. Sorry. Cool. Just like we don't have a product rule for antiderivatives, we also don't have a quotient rule for antiderivatives. So again, if you're tasked with something like find g of x given g prime of x, so if g prime of x is equal to, what have I got here? So let's do x squared plus x minus 5 over the square root of x. To find the function that this is the derivative of, or that, right, where this is the derivative, I need to simplify this first. I can't just antidifferentiate each part individually and say that's my answer. I have to do some simplifying. I guess what I should say is you can't use the power rule unless you have just x to a power and nothing else kind of around it, right? This x squared isn't just x squared, right? It's x squared plus the stuff divided by root x. It's kind of really stuck with this. But I can rewrite this. I can rewrite this as x squared over the square root of x plus x over the square root of x minus 5 over the square root of x. And I can rewrite each of those. Well, I can subtract the powers. X squared divided by x to the 1/2. 2 minus 1/2 is 3/2. So that's x to the 3/2. And x to the first divided by x to the 1/2. I subtract the powers, and I get x to the 1/2. And 5 divided by x to the 1/2, I get 5 times x to the negative 1/2. And now that I've written all of my terms as just x to a power and nothing else kind of attached to it, I can now say, oh, well, that's my derivative. I can anti-differentiate to find g of x by using the reverse power rule. So I'm going to get x to the 3/2 plus 1, which is 5/2, divided by 5/2. Now, typically what we start doing is instead of writing divided by 5/2, we end up saying, well, I know I'm just going to flip and multiply. So instead of dividing by 5/2, I'm going to multiply by 2/5. And similarly here, I'm going to get x to the 1/2 plus 1 is 3/2. And dividing by 3/2 is the same as multiplying by 2/3. And then finally, I'm going to get 5 times x to the, so negative 1/2 plus 1 is positive 1/2. So I'm going to get x to the positive 1/2. And then dividing by 1/2 is the same as multiplying by the reciprocal, which is 2. And I suppose we would simplify this as 10 plus 2. And that would be our answer. Again, please do jump in if you have comments or questions. I know it's day one, so everyone's kind of like, no. Oh yeah, let's look at this next one. This next one's a little bit more interesting. So things start to get a little more complicated when we start having things that kind of look like a composition of functions. For example, let's say our function was this. F of x is e to the 2x plus sine of 3x plus secant squared of 4x. And I want to find the antiderivative. All right, so I kind of think of this as almost like, it's kind of like the chain rules involved here is how I want to say it. So I'm pretty sure the antiderivative of e to the 2x is something like e to the 2x. I would probably even write down e to the 2x. Okay, but now here's the deal. The derivative of this is supposed to equal this. Can someone tell me what the derivative of e to the 2x is?
E to the 2x times 2.
Exactly. There's no times 2 up there. So what do we do to adjust for the times 2 that we know we're going to get?
Divide by 2.
Exactly. So typically what I see happening here for these problems where we have like something times x instead of just x is we typically end up dividing by the derivative of this stuff inside the exponent or inside the trig function. So we're dividing by 2 instead of multiplying by 2 like we would if we were using the chain rule. And here, for the antiderivative of sine of 3x, well, the antiderivative of sine is negative cosine. So it's going to be minus cosine of 3x. And for the same sort of reason, we're going to divide by 3 here, right? The 3 is the derivative of 3x. And the reason we're dividing by 3 is because the derivative of cosine of 3x, or negative cosine of 3x, would be positive sine of 3x times a 3 because of the chain rule. And that 3 that you would multiply by has to cancel out with the 3 down there to get just sine of 3x. All right. So what function has a derivative that's secant squared?
Tangent?
Yeah. So we know it's going to be kind of like tangent to 4x, except the derivative of tangent of 4x would be secant squared of 4x times 4. So we need to divide by 4 so that it comes out right. Yeah, so that's pretty typical. If I said, I'm trying to think, I feel like I've got another one there. If I said g of x is equal to, oh yeah, let's do that. Let's do, yeah, secant of 5x plus 9 times tangent of 5x plus 9. Okay, so I'm looking for a function whose derivative is secant of 5x plus 9 times tangent of 5x plus 9. What's a function whose derivative is secant times tangent?
Secant.
Right. But it's not just secant, right? It's secant of what?
5x plus 9.
Exactly. And now here's the same thing that's happening again, right? The derivative of secant of some stuff is secant of the stuff times tangent of the stuff times the derivative of the stuff. So if this was my incorrect answer, my incorrect derivative would have a multiple of 5. But I don't want that multiple of 5, so I divide by 5 so that I can divide this by 5. So basically, if your antiderivative is off, or I should say, if you think you found the antiderivative and you take, oh sure, just one second, Kayla. If you think you found the antiderivative and you take its derivative and you get back your function, except you're off by a constant multiple, you divide by that constant multiple to adjust. The reason, Michaela, it's secant is because the derivative of secant is secant of tangent, is secant times tangent. So I should really say the derivative of secant of x is secant of x times tangent of x. So the antiderivative of secant of x times tangent of x is secant of x. And the antiderivative of secant of stuff times tangent of stuff is secant of stuff. And then we had to divide by 5 because when you take the derivative of this using the chain rule, you end up multiplying by the derivative of the insides, which is a 5. We don't want a 5 because there isn't a 5 up there in front, so we divide by 5 to adjust for that. Hopefully that clarifies things. Cool. So there's just one other specific thing I want to talk about, and then I'll try and throw, I know I've only got like 3 minutes, but I'm going to throw one initial value problem at you guys just so you can start doing those types of problems too. So what about this function? F of x equal to 1 over x. Oh, sure. Let's make it a little more interesting. Sure. What's the antiderivative of 1 over x?
The natural log of x.
Right. And now we're gonna adjust that in just a second. But yes, you are essentially right. And does anybody remember a function whose derivative is 1 over x squared plus 1? Yes, you're right about the absolute value. Yeah. What about this part here?
Oh, arctangent.
Yeah. And that's just kind of one you have to memorize. You're right, Michaela, about the absolute value. It is the natural log of the absolute value of x. And the reason for that is that, right, for 1 over x, x can be positive or negative. But for natural log of x, x can only be positive. But we want those to kind of have the same domain, so we end up making it natural log of the absolute value of x. So x can be positive or negative. The actual explanation to that is a little bit more deep, but that's really kind of the actual reasoning behind it, is that we need this function and its antiderivative to have the same domain. Yeah. All right, I know we only have a minute, but I do want to show you guys this one more thing. So let's say we had this differential equation. dy dt is equal to 2e to the 3t, and y of 0 is equal to 1. Or people might also phrase this as y equals 1 when t equals 0. This is the nicer way of writing it. This is the way where it's a little bit harder to see what's happening. So we want to find the function, the original function. Meaning we want to find the antiderivative, right? I'm telling you the derivative, dy dt, and I'm asking you to find y of t. The original function, also known as the antiderivative of the derivative. So we're going to antidifferentiate this. So we're going to get that y of t is equal to, the antiderivative of this is 2e to the 3t divided by what?
3.
Right. And then plus c. So typically we'd be done, right? We'd be like, okay, we antidifferentiated, great. But for an initial value problem like this, where they tell you what the value of the function is at some particular input, you then have to take that input, put it into what you've got, and solve for the constant. So for initial value problems, also called particular value problems, you have to find, or I should say, you have to find the particular value of the constant, not just leave it as an unknown. So we're going to plug in 0 for t and 1 for y of 0. So here, this is going to be y of 0, which is 1. And here, t is going to be 0. So you're going to get 2/3 e to the 0 plus c. So e to the 0 is 1. This is 2/3 times 1. So you get 1 minus 2/3 equals c. So that c is equal to 1/3. And now I will say, although we found all the information, we haven't actually written the final answer. After you find c, you have to go back and write what y of t is with the actual value of c. So our final answer would be y of t equals 2e to the 3t over 3 plus our c, which is 1/3. And that would be the original function, aka the antiderivative.